Hi, this is Mrs. LaBarbera. This is AP Physics Mechanics C. Today's topic is circular satellite motion. The objectives are: no, gravity is the only force acting on a satellite. Gravity provides the centrifugal force to keep the satellite in orbit. Total mechanical energy of the launched satellite is constant. Know the relationship between circular speed and escape speed. Understand circular speed of an orbiting body is dependent on the radius and the mass of the planet, not the mass of the object. Be able to derive circular speed, escape speed, and total energy, and be able to relate the radius, circular speed, orbital period, and total mechanical energy of a satellite in a circular orbit. Satellite motion. A satellite is a projectile that is launched at a great speed so that it does not land on Earth but goes around Earth. Trajectories 1 through 7 show the effect of increasing the initial speed of a launched projectile. Trajectories 1 and 2 would be completed if Earth were a point mass at CH1 of its foci. Trajectory 3 to 5, those are called closed orbits, and they are ellipses. As a matter of fact, trajectory 4 is a special case because it is a circle. On the other hand, trajectory 6 and 7 are open orbits. For this path, the projectile never returns to its starting point. They are escaped. The total energy of these two projectiles in path 6, 7 are greater than 0. Satellites are in circular orbits. So a circular orbit is the simplest and an important case because artificial satellites as well as planets around the sun have nearly circular orbits. Since the only force acting on a satellite in a circular orbit around Earth is the Earth's gravitational attraction, which is directed toward the center of the Earth and hence toward the center of the orbit. The satellite is in uniform circular motion with constant speed. So acceleration is toward the center. Remember, if acceleration is going that way, it's speeding up. If acceleration is going backwards, it's slowing down. But for satellite, acceleration is going toward down. You only have centripetal acceleration, no tangential acceleration. So satellite is in circular orbit. Its acceleration is always perpendicular to its velocity, so the speed is constant. There's no tangential acceleration. Circular speed, we call it VR. That's the speed at radius r from the center of the Earth. To find a constant speed VR of a satellite in a circular orbit with radius r measured from the center of the Earth, we need to use the second law, Newton's second law, F net equals to ma. For a satellite, the net force is just gravitational force, and its acceleration only is centripetal acceleration because its speed is not changing, it's only changing direction. So Fg equals to mac. Fg, according to Newton's law of universal gravitation, is gm over r squared. Mac is Vr squared over r. From here, we can solve for Vr. From this equation, what can you conclude? The relationship shows that we cannot choose the orbit radius r and speed v independently. One thing determines the other. For a given radius r, the speed for a circular orbit is predetermined. The larger the orbit, the slower the speed. The equation also shows that the motion of a satellite does not depend on its mass. There is no mass in this equation. Any satellite launched in the same orbit will have the same speed. Radius, period, and speed in circular motion. So let's take a look. For object in constant velocity in a circle, v equals to 2 pi r over t. So from here, we can figure out t equals to 2 pi r over v. We already know what v equals to. In a circular motion, it's gme over r. You can derive this, setting up F net equals to mac. And F net is gravitational force equals to mac. That's how you derive this. You need to know how to derive this, okay? And so we substitute this VE here, we get T equals to 2 pi r 3 over 2 divided by GM. So the bigger the radius, the longer it's going to take for the satellite to go around. So this equation shows the larger the orbit corresponding to a slower speed and longer period. Both the International Space Station and the Moon are satellites of Earth. The Moon orbits much further from the center of the Earth than does the space station, so it has slower orbital speed. Take a look. Here's the International Space Station, much closer to Earth. It has a period 93 minutes and has a speed 7.7 kilometers per second. On the other hand, here's the Moon. It's much further, has much less speed, and takes much longer for it to go around Earth. Weightlessness. An astronaut on board a space shuttle is a satellite held by Earth's gravitational attraction in the same orbit as the shuttle. So in a sense, the astronaut is falling with the shuttle toward Earth. The astronaut has the same velocity and acceleration as the shuttle, so nothing is pushing her against the floor or the walls of the shuttle. So the astronaut is in a state of apparent weightlessness, as in a freely falling elevator. Even though gravity is acting on the astronaut, but astronaut cannot feel the force because there is no contact force acting on the astronaut. You can only feel it when you're in contact. Total mechanical energy, E equals to K plus U. So for circular speed, we already know V equals square root of GME over R. And E, total energy, is kinetic plus potential. Kinetic equals mv squared. V squared equals this according to that equation. And here's the potential energy. When you add it, this is just half of the second term. A positive half of plus a negative whole give you a negative half. So what does this equation tell you? The total mechanical energy in a circular orbit is negative and equals a half of the potential energy. Increase the orbital r. As r increases, this total number becomes less negative. Hence, the total energy actually increases, right? If the satellite is in relatively low orbit that encounters the outer fringe of the Earth's atmosphere, mechanical energy will decrease due to negative work to overcome friction. As a result, the radius will decrease because E decreases, so this R has to decrease, becoming more negative, and eventually satellite will hit the ground or burn up in the atmosphere. Escaping speed. To escape the Earth means its potential energy reaches maximum 0, and the kinetic energy to escape, the minimum kinetic energy has to be 0. So the minimum speed required to escape is E total equals to 0. So you said E total equals to 0 means kinetic plus potential energy at radius r from the center of the Earth equals to 0. So from that point, what is escape speed? That's square root of 2 times its circular speed. So the escape speed from a spherical body with radius r is square root of 2 times greater than the speed of satellite in the circular orbit at that radius. Let's take a look at this example. Suppose you want to place a 1,000-kilogram weather satellite into a circular orbit 300 kilometers above Earth's surface. What speed period and radial acceleration must it have? So since this is 300 kilometers above the Earth, remember the distance has, in all the equations, has to be from the object to the center of the Earth. So you have to add these two numbers together to find r. That is your r. Then the speed, you can use the equation. For speed, gme over r, that's what you have. To find the period, you can use 2 pi r over v. And to find acceleration, it's a centripetal acceleration, v squared over r. How much work has to be done to place this satellite into orbit? The work equals to changing energy. So you have to find energy on the ground and energy in that circle. So E2 at that circle, the total energy, remember we did this before, is negative gme over 2r. And on the ground, that energy is just the potential energy before it was at rest, right? How much work to launch from E1 to E2 to increase its energy, the work equals the change in total energy. So the total work done has to be 3.26 times 10 to the 10 joules. How much additional work would have to be done to make this satellite escape the Earth? So now this becomes E2. This is the initial energy. The final energy is 0. So what's the energy difference? Would be positive of that, right? E3 minus E2, the final energy escape is 0 minus this number, which is a negative GMEM over 2R, so that's 2.98 times 10 to the 10 joules. Test your understanding. Your personal spacecraft is in low altitude circular orbit around Earth. Air resistance from the outer region of the atmosphere does negative work on the spacecraft, causing the orbital radius to decrease. Does the speed of the craft increase, decrease, or remains the same? Remember, the orbital speed equals to GME over R. As R decreases, what's going to happen to V? It has to increase, right? Let's see what's the takeaway for this lesson. We know gravity is the only force acting on the satellite. Gravity provides centripetal force. This is very important concept. This is how you derive the circular speed, how you derive the circular speed. And from there, you can derive the total energy as well. So the total mechanical energy of a launched satellite is constant. So that's how you can figure out the speed, escape speed, and so forth. The relationship between circular speed and escape speed. Remember, escape speed is square root of 2 times the circular speed. You can also derive that by setting the total energy equals to 0 to find escape speed and see how it's related to circular speed. So you should be able to derive all that, all right? Understand the circular speed of orbiting body is dependent on the radius, how far it's away from the center of the Earth, and the mass of the planet, such as Earth, not the mass of your satellite at all. Be able to derive circular speed, escape speed, and total energy. How do you derive it? This F net equals ma. F net is gravity. And A is centripetal acceleration. You have to set those equals to each other. That's how you find the circular speed. And from there, you can also find escape speed and total energy. You have to be able to relate radius, circular speed, orbital speed, and the mechanical energy of the satellite in the circular orbit. So the essential equation is this: V equals to 2 pi R over T, because it's constant. V is constant. Last example. An Earth satellite in a circular orbit with radius R and the period T. What is the period of an Earth satellite in a circular orbit of radius 4R? How is T related to R? Remember the equation we derived? T is proportional to R to the power of 3 over 2. So R increased by 4 times. So what is 4 to the power of 3 over 2? That is 8. So the answer is just 8T. And that's it for today. Thanks for watching.